Hello, everyone. This is the 7th Race Online seminar. Today, Susanna will present graph neural networks for role discovery. Susanna, you can start.
Thank you very much, Georgios. Yes, so today I'm going to give this presentation about overview of two topics which are really relevant for my research at the moment. So we are going to have a bit of an introduction. Then we're going to go through a very high-level overview of graph neural networks. Then we're going to move to another topic that is Graphisomorphism and the Westfaller Element algorithm. And of course, we are going to figure out what these two ideas have to do with each other, and then some concluding remarks. But let's get started. We already talked a lot about the tools you have to analyze the structure of a given graph. And for example, if you want to divide the nodes that are in there according to some criteria, you can have, for example, some community detection and some role discovery. And as it is the case with a lot of tools out there, there are a lot of slightly different versions of carrying out a specific task. And what we are going to focus on today is deep learning with networks applied to the discovery of roles in graphs. And I don't want to spend a lot of time revising the differences between the communities and roles, because we already went through them. But I have my usual image of an organizational graph with relationships between employees of a company, where you can see that on this side, the colors encode, for example, the departments. Whereas on these other sides, the nodes are color-coded according to the roles of the employees, which in this case might be the job title, let's say. Let's move on to something new. So as most of you already know, there has been in recent year a lot of progress in the field of deep learning. And for example, we can mention recurrent neural networks, convolutional neural networks, which are used respectively to operate on 1D and 2D data. That is, for example, sequences of words and images. And of course, the same ideas has been applied to graphs too, and the result is called graph neural networks. However, they have a slightly different architecture, which is required because of the natures of graphs that are not Euclidean. Nevertheless, GNNs are nowadays widely used with success for a wide variety of tasks, such as classification, graph classification, or graph representation learning more in general. And I don't want to get lost in details here, but I wanted to give a brief overview of the idea behind graph neural networks, which is called neural message passing. And the principle here is that our objective is to learn representations for the nodes in a graph. And these representations are derived from some features that belong to the nodes, but are exchanged between them along the edges that are present in the graph. So when a node is constructing its own representation, it will use its own features, but also the features it receives from its surrounding. And to make it a bit more formal, there are two main steps in this process. The first one is the aggregation, and the second one is the update. With the aggregation, what happens is basically that the target node for which we are learning a representation collects some extra information from the nodes he is connected to. And then in the update step, this information is used to update the node representation. And as you can see here on the slide, I have a more formal equation that shows this process. So we have that the update is done. The update for the embedding and time k+1 is derived from the update of the same node at time k, but also from the embedding some time k of the coming from the neighbors of the node we are considering. And this HE here is usually called the hidden embedding of the node. And I have an example here, so you can see a pretty simple graph with 6 nodes here. And what happens is that if we wanted to update node A, we will do it based on the aggregated information that comes from A's neighbors, that is B, C, and D. But in turn, the representation of B, C, and D will depend on their own neighbors. So step after step, we kind of build this tree that represents the flow of information through the graph. Okay.
Can I ask one question on this side?
Yes, of course.
Yeah, so this aggregation that happens, is it like, at one time step, all of this information gets aggregated from each of the neighboring nodes, or it is, for example, in the first time step, let's say B, C, and D get the aggregated information from the first layer, and then the second time step, A gets the aggregated information from B, C, and D, and so
on? Not sure I got your question, but at each time step, a node's representation is updated based on the information coming from his one-up neighbors.
Okay, so I mean, this aggregation time is this is one time step, I would say.
Yes, so in each time step, you have one update and one aggregation and one update.
Okay, thank you.
Welcome. Okay, then, as I was saying, we are now moving to another topic, which at first might seem totally unrelated, that is Graphisomorphism. And the reason I'm doing this connection is because there is a pretty evident parallel between neural message passing and the basic idea of the Westfaller Element algorithm, which is used to assess whether two graphs are isomorphic. But of course, what does isomorphic mean? I have an example here, but the formal definition is that a pair of graphs is said to be isomorphic if the nodes are the same and the edges and the missing edges are preserved. That is, given two graphs, they're isomorphic if there is a B injection that basically maps all the nodes in the one graph to all the nodes in the other graph. So let's look at the figure here. We have this graph and this other. And what you can see here is that this node up here maps to this node down here. And you can do a similar reason for all the others. At the end, you see that they are the same graph, just plotted in a different manner. Okay, so Graphisomorphism is a pretty cool task, but even though it is used quite a lot, curiously, we don't know the complexity of the task. But just the same, it is used for applications such as, for example, network alignment in bioinformatics applications, or even for counting graphlets where you want to have an higher level picture of what is going on in the graph on the structural level. But why is Graphisomorphism and as a consequence, graph neural networks relevant to role discovery? The answer is that Graphisomorphism at the end of the day basically requires you to find a mapping between the nodes of two graphs. And finding this mapping implies that you have to figure out which nodes on both sides are structurally equivalent. That is, which nodes have the same function, that is the same role. Okay, And then I'm going to move on to this algorithm normally known as the Westfaller Element algorithm, which is the one most commonly used for Graphisomorphism. It was originally presented in the late 60s by two scientists from the URSS, which published a paper that is available online. It is in Russian, but there is an English translation available. And the main contribution is this paper is translating a graph into a canonical label such that if two graphs are not isomorphic, then you are sure to get two labels which are not equal. And the idea is exactly this one, that is, given two graphs with the Westfaller Element algorithm, we can assess if they are not isomorphic, but if we end up with the same label, we cannot say anything about them. So in formal terms, the Westfaller Element algorithm provides a necessary but not sufficient condition for Graphisomorphism. And in its original version, it works like this. So given a graph, we start by assigning an initial label to all of his nodes. Then for each iteration, the labels of all the nodes are updated by hashing the label belonging to the node, but also the labels coming from the neighbors of the node. And we go on like this iteratively until we find a stable condition where the labels no longer changed. And then you can use these labels as a fingerprint of what is going on in the graph. I have an example here, which I took from an article written by an author with quite a lot of publication in this topic. It's available on Towards Data Science, and you have the link here. And as you can see, we start from this graph where all the nodes are blue. And I would like to make a note here. I'm going to use the terms labels and colors interchangeably because traditionally the Westfaller Element algorithm is also known as a color refinement. But anyways, after the first update, what happens is that, for example, the yellow nodes get a new label that is derived by hashing its label at the previous type step, but also the labels of its neighbors. And we go on like this until we get to this condition and the fingerprint I was referring to before. And the same is done from this other graph here, which was the sample I used before. And as you can see, these two graphs are isomorphic, and as a matter of fact, we get two fingerprints. That is, we end up with two canonical labels that are equal. Okay.
So one quick question.
Yes.
So is this like algorithm, is it like an isomorphism test for these two different graphs?
Can you repeat the question? Sorry.
Is this like I forgot the full name of the algorithm, but is it like an isomorphism test for different graphs, like, you know, to see whether they're isomorphic or not? Because like when you apply the algorithm on the top graph and when we apply the algorithm on the bottom graph, then what we reach in the conclusion that like these two graphs are isomorphic in a sense.
Exactly, it's for comparing graph, but as a disclaimer here, you end up with the same label because indeed they are isomorphic, but I'm gonna come back to this thing because, as I say, the condition is necessary but not sufficient.
Okay, thanks.
No worries. Okay, let's go on. This algorithm, it's pretty cool. However, there are some limitations. Not only it is as a condition necessary but not sufficient, but it is also known that there are some specific classes of graphs with some specific properties that even though they produce the same canonical labels, canonical label, they are not isomorphic. So for example, you see here that we have two graphs, G and H, And with the traditional version of the algorithm, you're going to end up with the same fingerprint from these two graphs, even though they are evidently not the same, since one of them is not connected. But why am I talking? A few years after Westfaller and Element published the original paper, extensions have been proposed. And basically, the idea is that we can make the algorithm more expressive and thus capable of capturing more complex patterns of interconnection by reasoning not in terms of nodes, but by operating on tuples of nodes. So we go from a one-dimensional version of the algorithm to a k-dimensional one. And even though things get a bit more complicated in terms of complexity, the more you increase the dimension of the algorithm, the more interesting things you can capture. And to make things a bit more graphical, you see here that basically when you work on the one-dimensional version of the Westfaller Element algorithm, you're basically reasoning in terms of nodes. Then if we move to a two-dimensional version, we are reasoning in terms of pairs of nodes, that is edges. But the true improvement comes from 3 upwards, because as you can see here, if I look at 3 nodes at the same time, then I am more aware of what is going on. That is, I know who my neighbors are, but I also know, for example, if they are connected to one another. That is, I can start to recognize the presence of structures such as a triangle in the graph. Okay, and it has been proven that the same limitations that I was mentioning before for the Westfaller Element algorithm in its one-dimensional version are valid for graph neural networks too. And as a matter of fact, graph neural networks are not more expressive than the one-dimensional version of the Westfaller Element algorithm. So in the same way that the Graphisomorphism test is not able in some specific circumstances to recognize graphs are not as not isomorphic, even though they are. GNNs, you can say, are not aware of some specific properties such as connectivity, but also bipartiteness and about the presence of structures such as triangles. And of course, the natural evolution of graph neural networks in this direction is as the Westfaller Element algorithm can be extended in order to operate not on nodes only, but on tuples of node, we can do the same from graph neural networks. So we update the representation of a node based on not only is one op neighbors, but also is 2 or even more op neighbors at the same time. And this idea has been present in the literature, but I mentioned this paper here since it applies this exact idea to role discovery, and they achieve some pretty good results. But I also reported this example, which they do in the paper, which they show that in this example, let's say we want to update A. For the one-dimensional version of the graph neural network that we saw before, you would normally just aggregate B and C representation. But if we go two-dimensional, we would first of all update B based on the representation of D and E. Then we would update C based on the features that belong to E. Then, and this is the step that is more crucial in my opinion, we update B and C because they are connected to one another. And only now we use B's and C's update representation to obtain a new representation for A. And this example here is a two-dimensional version, but of course you can go higher. And in the paper I mentioned here, they do experiments with the 2-op GNNs and 3-op GNNs. And as I was saying, they have some pretty nice results. So I have some concluding remarks, and then I would love to have a bit of a discussion with you. So first of all, as I hope I explained today, there are many directions to be explored in the application of deep learning with networks when it comes to the discovery of roles in graphs. And one of the tools that are most promising is graph neural networks. We had a bit of an overview of the overall idea behind the graph neural networks. But I would like to point out that today I presented that an interpretation of graph neural network from the point of view of Graphisomorphism. And this helped us understand some of the limitations that are there, but we can overcome. Still, there are other ways to look at graph neural networks. In particular, you can, from a graph signal processing perspective, look at them as, for example, low-pass filters, but of course, there are also adaptation of convolutional neural networks. But the idea is that there are different perspectives on the matter, and each of these perspectives is useful because it helps us understand the strengths, but also the weaknesses and the limitation that we are facing. Then another remark, which I made last time as well, is that when you're reasoning in terms of graphs, most of the time it's more than enough to look just at your one of the neighbors, that is at the nodes you are directly connected to. And of course, they can give you a lot of extra information, which is useful for whatever task you're trying to achieve. But more and more often, with things getting more and more complicated, it's quite almost always a pretty good idea to not stop at your direct neighbors, but also to look a step further, because I mean, of course, it's easier to just be in touch with your friends, but the friends of your friends most probably can be relevant for whatever you're doing as well. Okay, and I have some references here. So I have the original article in Russian. Then there are a couple of books on, there's a book on graph representation learning, which is pretty good. And the paper I was mentioning that is one of the first one to explore this idea of higher order graph neural networks. And then another resource, which I found pretty useful if some of you are interested. Okay, and that's it by my side. I hope we can have a nice discussion.
Thank you, Susanna, for your presentation. Do we have any questions from the participants? Okay.
Actually, I do have a question.
Mm-hmm.
Yes, please.
Excellent. So thank you for your presentation. And I was wondering, okay, I assume that in order to test, let's say, the algorithms that you're developing, as well as the state of the art, you're utilizing some data sets that are quite common in the domain. But have you put some thought, or let's say, have it come up in discussions, how this sort of representation and algorithms could be used in the Internet of Sports scenario, in a sense, like in a network of wearable devices or something like that?
Yes, of course. So as I was saying, Graphisomorphism is by itself super relevant, because it can be used, for example, to count subgraphs such as motifs and graphlets, which are super useful when you want to gain insights into how a graph is organized. And then as a consequence, once you have an idea of what is going on in terms of the structure of the graph, you can, for example, let me think of an example. I mean, you can take advantage of this insight, for example, to have to be more aware about how the influence gets spreaded in a distributed algorithm, for example, and for example, you can use them to do anomaly detection. So even though what you presented today might seem a bit unrelated because it's pretty low level, it indirectly has a kind of lot of effects on the higher level tasks that are normally used in the analysis of the IoT and thus the Internet of Sports.
Well, thank you, Susanna.
Thank you for the answer, for the question.
Anyone else?
Yeah, may I have a question?
Yes, of course.
Okay, so, well, first of all, thank you very much for the presentation, very interesting. But like, I was wondering regarding the concept of graph isomorphism, because basically graph isomorphism
I cannot hear you.
And if you have like, oh, sorry, can you hear me now?
Yes,
Thomas?
I think I lost you for 10 seconds though, so if you can repeat the question, it would be great.
Okay, can you hear me now?
Yes.
Okay, great. So what I was wondering that basically graph isomorphism is a very strong requirement. It's a very strong property for graphs, and so like I was wondering how can you apply it to very large networks that are very unlikely to be isomorphic,
Okay, that's actually a pretty interesting question. And yes, for some applications, you want graphs to be isomorphic, for example, when you're counting motifs or subgraphs in general. But for other applications, and first of all, role discovery, this idea of one-on-one mapping is a bit too strict. But there are relaxations of this topic which you can accommodate for with some adjustments. So
yeah,
so,
I see.
yeah, that's the idea.
Yeah, I think I understood. You can basically relax it. And I was wondering, basically, do this like graph neural network and like K-hop graph neural networks come into play like for role discovery, for example? Because as you mentioned, like you may have networks with same roles. For example, I think about like soccer clubs that may have a different graph structure, but they may have the same roles. So like basically you can use graph neural networks and these K-hops graph neural networks to discover roles in this way.
Exactly, and this would be a specific case of the node classification task, meaning that you want to classify nodes based on their structural function in the graph. And another thing which is pretty commonly used as an example is for the analysis of proteins, where you want to understand each piece what is doing in the overall structure.
I see. Thank you very much.
Thank you for the question.
Do we have any other questions? Okay, so it's time to close the session. So thank you everyone for participating in this 7th Race Online seminar. And thank you very much, Susanna, for the nice presentation you did. We will meet again in 3 weeks with the 8th online seminar for this year.